Welcome back. Let's get stuck into factor loading matrices and rotating solutions and what does all of this really mean. So a factor loading is the relationship that each variable or item has with the factor, right? So you have a factor, you have an item. What is the relationship that that item or variable has with that factor? Now, you can take different solutions here. The first solution can typically be an unrotated one. So in the initial solution, what this means is each factor selfishly grabs the maximum amount of unexplained variance. So you have the first factor that's extracted and the best possible line of best fit through the original variables, and it seeks to explain the maximum amount of variance that's there. It gives the best single factor summary of the variance in the whole set of items. So all variables will tend to load strongly onto factor one because it does it sequentially. So it's first factor one is there, and it takes up the lion's share of the variance. Then you have factor two, and it seeks to maximize its own eigenvalue by trying to explain as much of the remaining unexplained variance as possible. And so each subsequent factor does the same until all the variance is explained. So imagine we have imagine we have 5 people and we have a cake, right? And so I am the first person on the cake and I try to eat as much as I can and I eat like half the cake. Then the second person has only half the cake to try to eat as much of that they can. They eat like a quarter of that, so then or half of that, so then there's a quarter left, and it goes on, and they keep partitioning smaller. So the point here in the analogy is we are the factors, right? Each person represents the factor, and the cake represents the variance that's potential variance able to be explained, and it's sequential. So the first person, because they have access to all the variance, can explain the lion's share with their factor, and subsequent factors explain the remaining variance. Now, you can also do something called rotating the solution. So a rotated solution is generally easier to interpret because you rarely actually see this unrotated factor structure that occurs. Many variables typically load onto 2 or more factors. And there's different types of rotations that can occur. And really, this is how we get the factor structure to explain the most amount of variance. That's what I want you to think of. We have the data that's there, and we're trying to account for that through the factor structure. Geez, I really love the hand analogies today. Hopefully that's helping. I think factor analysis is a lot of shapes and mathematics there, so maybe that's why it's there. So you have orthogonal rotation. Now in Jamovi, this is called Varimax, just because why not learn 2 words for the same thing? So we have orthogonal, which is Varimax. Try to keep those together. Orthogonal is in the literature. Varimax is what Jamovi calls it. Minimizes the factor covariation, and it produces factors that are uncorrelated with one another. So the factors aren't related. And then you have oblique, which is called Obleman in Jamovi, and it allows factors to covary. So it allows for correlations between factors. So when you do your analysis, you can just look at the factor structure and say, are they related? Are they not related? Oh, they're related. Okay, maybe an oblique rotation would have been better. Are they not related? Okay, orthogonal is a good choice. So you can actually use an iterative process to sort of reassess as you go. And I think a useful way is oblique, Obleman. They both start with OB, so that's how you sort of know oblique and Obleman are the same. Orthogonal and Varimax, I'm lost there. You just need to connect those 2 together in Jamovi. But I guess it's not Obleman, so I guess it's Varimax if that helps. So how do you choose between orthogonal versus oblique? So this is essentially, are you expecting the factors to be related or unrelated? In the first instance, that's how you can direct your choice. So if it's related, choose the oblique. If it's unrelated, choose orthogonal. If unsure, just choose oblique and then switch to orthogonal if the correlation between factors is essentially smaller than 0.3. So assume that they're related, and if you find their factors are not really correlated with each other, which you can just do in a correlation table, then you can switch back. So you can try both and just see which solution is most interpretable. Now, so interpretability matters, and hopefully that's the driving point, but please don't just go with the solution that has the best factor loadings. You want to think it through. So be guided by the theory, logic, and common sense, but really it's in logic that's there from your understanding of the evidence, and ensuring that every factor needs to be interpretable. That's the key takeaway. So interpretable in a sense where you can say this factor represents this and these items meaningfully load onto that factor. Remember, loading is that relationship that items have to factors. What's a word of caution? Well, you've noticed already it's a subjective process, as I've said, through the process of check if your factors are related or not, and then you can flick back and forth. But this does mean that you can be swayed to see what you want to see. Be aware of this, try and avoid it. If the evidence is suggesting a different solution that fits the data better, try and see if this also makes sense and what's going on. But it's possible that there's more than one good solution, or perhaps the literature says something and your data says something else, and maybe it's related to the fact that the literature is on a certain type of sample and your data is on a different type of sample, and so you have different factor structures that emerge. And so it is possible to have more than one good solution. So for example, we see this in personality research. There's a 3 and 5 factor model, even 16 factor models that work. So really, there's no one perfect solution. Justification matters, and it may vary as a function of the data or the population that's there. And so these are important things to consider when interpreting. Keep it simple. The simpler your factor structure, the easier it is to interpret. Some additional criteria is each variable should load strongly, about 0.4 or higher on only one factor. Each factor should have 3 or more strong loadings. The more it has, the more reliable it will be, and we'll talk more about that later. But really what I mean by that is it should have multiple items loading onto the factor, so at least 3. Most loading should be high or low, few intermediate values. So they either load or they don't load is the key takeaway with your factor structure. So when you're refining your factors, you may need to eliminate some items to refine your factors. Again, this is a subjective process, and often researchers work with one another to see what makes sense and stress test their ideas. And that's why we present at conferences as well, to say, here's some analyses, here's what I've done, here's what I think, what do you think? And some points to consider for each item is how big is the item's main loading? So it should be at least 0.4 onto the factor, the primary factor. How big is its cross-loading? So if it loads onto another factor as well, that should be below 0.3. And what is the meaning of the item? What contribution does it make to the factor? Does it make sense that it would belong to this factor? These are really the key critical points to take away when thinking about whether items load onto factors. So you want to eliminate one variable at a time, then you rerun the factor analysis and you see how the model goes. So don't make big changes at once, just change one thing, rerun it, and see how it goes over time. So the Comrie and Lee offer the following guidelines for assessing factor loadings of an item. Less than 0.32 is poor, greater than 0.45 is fair, greater than 0.55 is good, greater than 0.63 is very good, and greater than 0.7 is excellent. But as you know by now, it's important to judge this in relation to other items in the factor. If most are loading excellently and the item in question is fair, that's a big gap in the loading. But if they're most are loading within the same range, then that's okay. Here at work so late that the air conditioning has turned off. It's still light though, but it's just late. So maybe that changes the audio. We'll see how it goes. So it is important to judge this, in relation to the items and the other factors. So the foundational question is the factor interpretable without the item? And so if you take the item out, is it still interpretable, or do you lose the interpretability of the factor? So what are the steps? You want to try both principal components and principal axis factoring methods of extractions. You want to run orthogonal and oblique rotations and test out the range of possible factor structures, so 2, 3, 4, n number of factors. Remove poor items one at a time, then rerun the analyses, and then check reliability analyses, which we'll cover more in next lecture. So what I want to do is do an example, and we'll see how this works for this context of this in action. So this is a student adjustment to university survey. I wanted to see how well students are adjusting to university. Participants responded to 12 items. Responses were on a 7-point Likert scale from strongly disagree to strongly agree, and the items were designed to capture academic stress, sense of belonging, self-regulated learning. So it could be questions related to, in the last week, how stressed did you feel, or I felt stressed about the transition to university from high school. I struggle with managing my workload at university, or for sense of belonging, I feel connected to my teachers, I feel connected to other students, I feel connected to the university. Self-regulated learning is I take initiative to watch lectures and keep on top of assessments. And so these are all the questions that could be the items that we're asking in the survey that are designed to capture these constructs. And so here are the following that are important to consider. Theory: is there good reason to ask this research question? So what's the question? What are is the factor structure in this questionnaire? What are the dimensions of say, student adjustment to university? Are there concrete dimensions there? Is the sample size sufficient in cases to variables ratio? We know we have 12 variables here, and we have 1,200 cases, so I blew this out a bit, but clearly it's good. And level of measurement, Likert scale with 7 response options, is that sufficient? Well, it's good because it allows us to make a more convincing argument that it's an interval measure, which is important for assumptions of factor analysis. We'll look at normality. So here's the data. I've plotted it for each of these measures. So the stress measures, belonging measures, self-regulation measures, 1 to 4, and you have the mean, standard deviations. And so you could also ideally plot this data, and you can see is it skewed? Is there kurtosis that's there? But ideally, it works best when it's normally distributed, but factor analysis can cope with minor violations of normality, right? So looking at this is useful, but obviously I often think looking at the histograms is even better to get a good sense of it. And so here, you can look at how the histograms are for each of the measures, the distributions, and you can see there's slight skewness in some, but largely there's some normal distribution for others, and these are the minor violations that can be addressed. Now, remember, for outliers and linearity, we can address this with scatter plots. So we can look at our scatter plots and see, are there any clusters of values that are outliers? Are our measures linearly related to one another? And so these can be addressed through the scatter plot diagnostics. And we can see here, it's all looking good in terms of here. I haven't put all of it because I couldn't really make the image large enough here on the slide, but I've just printed or produced the code for part of the diagnostics. Factorability, hopefully Bartlett's significance test is there, and the KMO is there. Is it significant? We do the chi-square test and we see, yes, it is. It gives a rounded p-value to 0, but it's very, very small. Is the KMO, where does that fit? And it says it's greater than 0.5 or 0.6, well, it's 0.8. So we know that that's good. So that's well above the range that we're looking for. So it indicates it is factorable. Again, we want to also have further evidence, so we look at correlation matrix. Are there clusters of correlations that are greater than 0.3? And we can see, hopefully you're pausing the video and maybe having a look at yourself here, because it's a bit of a skill to learn, but you can see there are clusters here of 0.3. There are certain clusters here of 0.3. Interesting, there's a stress 4 and belonging 2 is a 0, and stress 4 and belonging 1 are 0. So that stands out a bit. And we can see clusters here as well, greater than 0.3. So it does indicate that it's factorable. So I'll keep that in the back of my mind. So factorability and linearity, right? So we have the factor structure you can look at here as well. So this is just the correlation matrix that's here, but plotted here with the graphs and the distributions. So that's all there. Test the assumptions of exploratory factor analysis. Can you do the analysis in your data? Yeah, the items are sufficiently correlated, sample size is more than adequate. Select your method of extraction. Are factors likely to be related? The factors could be related. We could choose oblique or Ubelmann rotation to assume related and then check the correlation between factors. If the goal is to identify underlying factor structure, we'll use principal axis factoring, which is a reasonable choice there. Remember, principal components, which is that dimension reductionality, principal axis factoring, identify underlying structures. That's what we'll do there. And so let's determine the number of factors. What is the data telling us here? We have to select the items that fit each factor name and define each factor. Do these make sense? This is sort of the key steps to take in the process. So let's have a look here at what we see in our scrape plot. Hopefully you're pausing and trying to assess what you see. I think it's reasonable that you see it's a 3-factor structure. It looks good. It's above 1, and we have that 3 structure. Looking here at these factors and the eigenvalues, we can see the first 3 explain the lion's share of the variance here, and then the remaining explain incremental improvements overall. And so here's our table of factor loading. So we have each of the items. We chose our 3-factor structure, and we can see that for stress 1, 2, 3, 4, they load onto factor 2, and none of the others seem to load onto it. For belonging 1, 2, 3, 4, that loads really nicely onto factor 1. None of the others load onto it very well. And for self-regulation 1, 2, 3, and 4, loads really nicely onto factor 3. So we have a really clean factor structure here, and no cross-loadings that are occurring, and so this would be something that you'd be happy with statistically. Now the question is, what do each of these items mean? Can we make an interpretable factor structure for each of these factors? What does factor 2 mean in light of these items, and do they make sense? Do they actually cluster together? Can we identify what that construct is? So determine number of factors. What is your data telling you? A 3-factor solution appears most interpretable. Select the items that fit onto each factor. So those are the items. And ideally, we're looking at the questions as well to name and define each factor. So does that make sense? So factor 1 represents sense of belonging. Factor 2 represents academic stress. Factor 3 represents self-regulated learning. So again, that is determined by looking at what the actual item is, what that question is saying. I have close relationships with my colleagues and my teachers and whatnot. So those are the questions you're looking at to see that they cluster together. And so remember I said that when we're talking about the whether the factors could be related or not, we'll start by assuming that they're related. Well, we need to test that. So we do that by looking at correlations between our 3 factors. And we can see that to what extent they are related. So here we see factor 1 and 3, 0.4 correlation, 2 and 1, negative 0.3, here 0.22. So at this stage, I'd be saying that maybe there's some correlation between some of the factors, but others maybe not as strong. I would actually rerun the factor analysis with the orthogonal rotation, so to assume that they're unrelated, and see if I get a cleaner factor structure. I know statistically this is pretty clean, like there's not a lot of cross-loading that's occurring, so I would just run it again just to see if it improves at all, but at the moment it's fine as is. And then we analyze the internal reliability. Do the items in each factor contribute to a reliable subscale? We need to ensure all variables are coded in the same direction. So we can calculate our alpha values and look at does academic stress, do all the items reliably measure what we think they measure? Same with sense of belonging and self-regulated learning. And we'll come back to this in the next lecture about talking about reliability and scales. So that's everything for today. What is factor analysis is really what we covered. So it's a family of multivariate correlational data analysis methods for summarizing clusters of covariance. That's the fancy term. Really, it summarizes the correlations amongst variables or items in a survey, but I've given you examples where it can be used in other contexts as well, like in genetics analysis. The common clusters called factors. They indicate underlying fuzzy constructs. So they allow you to measure some construct that's there within the data. How do you do it? Well, you examine assumptions, you choose the extraction method and rotation, determine the number of factors, select the items, name and describe the factors, examine correlations amongst factors, and then you analyze the internal reliability next week and compute composite scores. I did show you a bit of a glimpse at what that looks like when you're doing internal reliability, but next week we'll go in a lot more detail as to how you do that, and also I gave a hint as to why we create composite scores and their utility. We'll go into that in more detail next week. What are the assumptions? You want to check your sample size in relation to the number of variables you have, at least 5 cases per variable, ideally 20. Check for outliers, check that your correlation matrix is factorable, and check for normality. And we talked about the types of factor analysis, including principal axis factoring, uses shared variance for theoretical exploration. principal components uses all variance for data reduction. Rotate, oh look, this is all the hand gestures in one slide. So we have data reduction, orthogonal for uncorrelated factors, oblique for correlated factors, and you have the rotations that are occurring there. The number of factors depends on the eigenvalues, so you want to look at the values above 1, and for the elbow in the scrape plot, the percentage of variance explained, so aim for 50 to 75, but I gave you an example where that wasn't met and it was still useful, how interpretable each factor is and how the factors fit with the theory that's there. Selecting the items depends on an exploratory factor analysis of a good measurement item. It ideally has a simple factor structure, so each variable loads strongly onto only one factor, and each factor has multiple loadings. So a variable loads strongly onto the factor, and then the factor has multiple loadings. So more loadings means greater reliability, and we'll talk about that more next week. Target factor loadings are high, so they're greater than 0.5, and the cross loadings onto other factors are low, less than 0.3, with few intermediate values, 0.3 to 0.5. So next week, we'll talk about psychometric instrument development, what concepts are and how to measure them, measurement errors, psychometrics, reliability and validity, and creating composite scores. But that's everything for this week. Hopefully you have a good sense of exploratory factor analysis now and what it means and how it works, what the assumptions are, and really you can walk away with a good sense of why we do it and how it's done. And so it's important to understand the relationships between these concepts. So it really, correlations are what underlie it, and hopefully you found it interesting. In saying that, have a lovely day, lovely week, and I'll see you guys in the next video.